what I'm going to do is, this is where we left off, and here's this type of stress depth envelope that we've talked about, where there's coupling or their lack thereof at the MOHO, depending on the relative rheology of the crust and the mantle. And so the next step here is to go back into the mantle, and I'll skip this. We can talk about this some other time. Is what kind of constraints do we have on the rheology of the mantle other than mantle convection? I mean, mantle convection is a great one, but we also have other constraints, and a relatively good one is from post-seismic creep. And so this is an example from a paper by Andy Freed looking at post-seismic creep after the Hector-Mine Landers sequence, concentrating on stations way out here, as well as stations in and around this area in here. And so the observed, let's see, make sure I get this right. The black ones are observed cumulative post-seismic displacements after 7 years after Hector-Mine, and the white ones are models which include just the post-seismic creep component. And it's the cumulative displacement and the azimuth of that. And you can see it works pretty well. And from that, because of the depth and spatial and time resolution, Andy concluded in a sequence of papers that you really need this creep to be in the mantle, and that it also gives you a constraint on the rheology of the mantle. And beyond that, it gives you a constraint on the conditions necessary with the elevating flow laws to be consistent with the creep rate. So this is the total displacement, and this is the years after the quake for this station way out here by Yucca Mountain. And so here's the evolution, and you can see it has this time-varying displacement versus time, which means that's a time-varying strain rate, if you like to think of it in that way. And these are the models that give, so the black line is a diffusion creep law with a grain size of 2 millimeters or so, and the dotted line is a dislocation creep law that gives about the same total displacement, but it's missing this big change in displacement rate. And basically the point after that is that there's a bunch of uncertainties here related to what the geotherm is and what the stress state is, what the background strain rate is, and all of that ties in to what the viscosity of the mantle is. And in addition to that, you also have to understand what the transient strain is, because the strains involved here are in the range of 10 to the minus 6 or something, or 10 to the minus 5. So they're very small strains, and that's a point where when you use these flow laws that we've been talking about, those are steady state flow laws. And so there's a perturbation on top of a steady state flow law, which is a transient creep response. And so here's a figure down here that shows this type of transient creep response for olivine. This is all a dunite deformed at 1100 degrees. And so here's strain on this axis, and the black guy is the strain. And so this is a paper from Prem Chopra, and what Prem did was he was running a deformation experiment, then he cranked the stress up to 400 MPa and just kept it constant. Then you see the displacement, or the strain, varying as a function of time. So if it was steady state creep, the strain versus time would be a straight line. But you see that it's becoming less and less steep with time. And so this is representative of a transient creep response that maybe some of you have heard of Berger's models and things like that explain that. So if you account for this transient type of creep response, and you can see right when you start the high load, you get a very, very high strain rate, which might be in the order of give you a viscosity 5 to 10 times smaller than the steady state viscosity. And after you account for that, these curves actually kind of nail not only the total displacement and the azimuth of the displacement, but also the time history, or the evolution in the strain rate. But there's a caveat to that, and you can see, look at how sensitive this is. It's kind of ridiculous. So here's the stress exponent of 3.25, 3.3. So we're talking really the third significant figure of the stress exponent as being something that you kind of have to worry about, which to me is kind of scary. I mean, I don't know how scary you guys think of that. So what your task is then, all right, is to evaluate this. So in order to create that, in order to get that, you really need to know a viscosity. And the viscosity gives you a prediction of what the water content and the grain size and the background strain rate would be in order to match those GPS observations. So what you guys are going to do is make this plot. So I'm going to teach you how to make this plot so that you can evaluate the same way that I did when I made this plot, that, gee, it actually looks like it works really well. And so part of the information that I'll give you is, in order, I don't want to get too involved with this, but these are two different grain size stress relationships that are, for all intents and purposes for this exercise, are the same. So the grain size stress conditions for a water content of olivine of 1,000 ppm in moles at a depth of 50 kilometers and 1,200 degrees C matches perfectly the GPS data. So what kind of independent constraints do we have on that? So that's an olivine flow law, and you say, well, it is perfectly consistent with the GPS post-seismic creep response if the temperature at 50 kilometers is 1,200 degrees C, which is consistent with the type of xenolith record that you would have in the basin range, and a water content of something like 1,000 ppm hydrogen per silicon, and a grain size of something like 10 to 20 millimeters. So what do the xenoliths show? So we don't really have xenoliths from exactly this place, but not too far away in similar locations. This is a paper from Lee et al. Looking at water contents. So the basin and range guy is this DH thing here. And this is something that must be super annoying to people. Water contents are either reported in weights or in moles. And so there's this conversion factor that you have to do in your head. And most people can't do that in their head because they aren't familiar with either of them. But so I always think about it, the material science type of people always think about it in terms of moles or hydrogens per silicons. And that's because that's how we measure it. Petrologists tend to measure it, well, they used to measure it by weight. Now they actually measure it by hydrogens per silicon and then convert it to weight. But be that as it may, a number in here, this is the concentration of water in olivine by weight per ppm. And this gives us something like 15, maybe 20. That's this line here for olivine. And the grain size from xenoliths from San Carlos, which if you look at something like one of these type of maps of seismic structures, maybe similar to the area that we're looking at, and you look at the grain size, and it's around 10 millimeters. So it actually kind of worked. So the temperature in the xenoliths is around 1,200 degrees. The grain size is around 10 millimeters. And the water content is just a little bit low. But for all intents and purposes, it nailed it. So what I want you guys to do is to build some intuition and make that deformation mechanism map. So I'll teach you how to do that. And then consider what would happen if you change the temperature, change the water content, and then if we have time or for further homework assignment, put it back into the context of a stress depth diagram. So we're talking about this down here, and then I just want you to be able to bring it up here and look at the MOHO for the importance of there. So just to give you an idea kind of what Andy's work suggests, he doesn't see evidence for creep in the lower crust, which suggests that there's this is a different place. This is the Parkfield segment. But there must be slip on a fault during the Hector Mine earthquake that perturbs the stress down in the range of 50 kilometers or so. And that stress pulse then diffuses away by viscous creep. If it had been shallow in the crust, you wouldn't see it spread out the same way you do. That's one of the reasons why you need it to be deep. And if the viscosity were wrong, you wouldn't see the amount of displacement that you do. So all that matches. So I just want you guys to then build some further intuition, and that will make you use, you can use either MATLAB or Excel or anything, because it's a really pretty simple manipulation of equations to make these plots. So maybe break up into groups of 2, and then I'll start writing up on the board just to give you the recipe. And it should probably, once you have the recipe, it should take you maybe 20 minutes to make this plot, something like that. And then we'll look at it, see if you end up with the same thing. If you can't, I can come around, or you can ask other people to help you out. And then we'll move on to the step diagram. I gave you some pertinent references that are on the B-space thing under a folder called Hirth tutorial or something like that. So to make this, the deformation mechanism map, what we're going to use are olivine flow laws. You can, I mean, I don't really care how you do this. I mean, it's simple enough that you could all do it if you have your computer. So the first thing you're going to need This is a review paper, yeah. So in B-Space, you should be able to find this paper as a PDF. So these are the laws with all the parameters that go into the equation. And so what I'm going to do first is just give you some really simple algebra to facilitate making the plot. So you guys ready to roll? So the total strain rate is the sum of the dislocation creep and the diffusion creep flow laws. And that's, these curves show you the stress grain size contour for a constant strain rate. And so you can see in this part of the place you have a strong grain size dependence, and then in this part you have no grain size dependence. This is dislocation creep, and this is diffusion creep. And then you can see here that there's some curvature to it. And that's because the total strain rate is the sum of the two. So at this point right here, to get a strain rate of, this is a strain of 10 microstrains per year. So 10 to the minus 6 divided by 3 times 10 to the 7 is whatever, almost 10 to the minus 14 per second or something like that. I don't know if I did that math right, but it's something like that. Yeah. These are in microstrains per year. So here, the strain rate of each comprises half of the total. So if you extrapolate these lines to this boundary, where both of them are 10 to the minus 12 or whatever, then the total strain rate will be 2 times 10 to the minus 12, because you have this sum involved. So the first thing we're going to do is draw this line on here. Okay? And so to do that, you just want to do something pretty simple. I'm going to rewrite these laws, and you're going to have to do a little bit more to make them work out right. So the way I'm going to write this is strain rate equals A times stress to the n plus B times stress over d cubed. Because I just want to get the form of the equation that fits these lines, or this line. So if I want to have a line that separates the fields where the strain rates are equal, all I have to do is say A stress to the n equals B stress over d cubed. Right? So stress to the n minus 1 equals B over A d cubed. And then stress equals B over A. Times d cubed to the 1 over n minus 1. Right? So that, you follow that? It's just really simple algebra. So that's the equation of the line in stress versus grain size. Right? So in Excel or MATLAB, you just need to make an array that is this equation. So what you have so there's a little bit more complicated than that. So it will take you more than 10 seconds to do it. It's because you have to calculate what A and B are using the flow laws. And so this is something that maybe you were going to do some model and you want to look up in the literature. So let's practice how you do that. Because people like me will screw up the way we present the data sometimes and make it really complicated, and then you have to make sure your A's and B's are right from this equation. All right? All right, so I'm going to get to that right now. So let's look at the full form of the equation. And I would actually recommend that you might even consider writing this out in MATLAB in this way. So the full form of the equation and then I think I'm going to sneak this in over here. So there's a concentration of OH to some exponent R, then A term, and then this term. Okay? So where do we get these parameters? So A will be, for dislocation creep, COH to the exponent R times A for dislocation creep times the exponential of E for dislocation creep plus P times V for dislocation creep divided by RT. What's that?
Write it down.
Yeah, so if you look in this paper, so we're going to do wet dislocation creep, which is right here. And what we're going to do it for, just it's much simpler, is we're going to do it for a constant concentration of OH. So for wet dislocation creep, A is 90. So this equation here. I'll call this A prime just to keep it separate from the thing that's called A in there. So dislocation creep. And what we're going to do this for is T equals 1200 degrees C, which is equal to what? 1473 Kelvin. one of the first things you always have to remember is you always work in Kelvin whenever you deal with the Arrhenius relationships. And we're going to do it for P equals 2 GPa, so equal to 2 times 10 to the 9th Pascal. R is equal to 8.314. Okay. A is, so this is the reason why the thing that people screw up all the time is this A term is basically a fitting parameter. So you have to make sure that the units that the person gives you A is the same as the units of stress and grain size and whatnot that you're dealing with. So A equals 90. E plus PV. So E, right over here, for wet dislocation creep, constant COH is 480 kilojoules. So if we're going to use joules, we need 480,000. So this Arrhenius term is going to be minus 480,000 plus PV. So that's 2 times 10 to the 9th times the activation volume for wet dislocation creep is 11 times 10 to the minus 6 meters cubed per mole. And then divide by 8.314 times 1473. So that's that term.
Yeah.
So all I'm doing is plugging the numbers in from this. So you should be able to set up something that says, I'm just plugging the numbers into this equation, right? It's not like I'm not doing anything that fancy. Right. So this is R. This is T. E plus PV is the activation energy plus P times the activation volume. What do you guys lost on? All I'm doing is trying to get you to realize you're going to just set up these variables to stick into equation and plot it. So in order to do this, you need to fill in these values. So for shorthand, instead of writing out all this junk, I just made a substitution that had a constant, and that constant was equal to this times that. Right? Do you follow that? You don't get that?
Well, it's just sometimes.
What's that?
Doing it while listening sometimes.
Yeah, okay. That's why it's a tutorial and not a lecture, I guess. Yeah. All right. So A prime then, right, equals 90 times, what's the concentration of water that we wanted to use? The COH we're going to use is 1,000. 90 times 1,000. We have to look up this R value.
What's the unit of the COH?
It's in hydrogens per 10 to the 6 silicon. Yep. R is 1.2. And then times this thing. So so I made an equation here, right? So what's that? This is, so here, let me go over this really quickly again.
Okay, listen up, people.
Listen up again. I'll just go over this really quickly again. Listen up. All right. So this is the full equation of the strain rate thing. I didn't want to write this all out, so I just made it a shorthand notation, because we're doing it for a constant water content and temperature and pressure. So a lot of this stuff just comes out, as you can think of it, as a constant, right? Does that make sense? And I'm going to call it A prime, just to. And the reason I did that was I wanted to just write out this equation, the A prime sigma to the n equals B times sigma over d cubed. And I wanted you to plot that equation.
Hold on. A prime is basically A times COH times
This Arrhenius relation.
times the exponent.
That's right. So A is this term times that term times that term.
That's A prime.
That's A prime.
Right.
Right. And then you can just, in your Excel file or your MATLAB file, you can set a variable and just say it is equal to this. Right? You're going to plot this equation. That's going to be this line right here. I used 11 times 10 to the minus 6. It is.
Oh, it's the wet just right here.
Yeah.
Okay.
Yeah. So you guys still lost? Who's lost? Oh, you got it. All right. So now you have to do the same thing for the diffusion creep one, because you have to calculate B. Yep.
So why is A prime doesn't include grain size?
Because there's no grain size dependence to the dislocation creep flow law. Right? Maybe that's not clear? So you... So you guys think you can figure... So what's B? Who wants to tell me what B is? So... All right. That's just this. So now we have to figure out B. So B, we just go to this line, wet diffusion for constant COH. So it's going to be this thing, 1 times 10 to the 6th.
So are we doing wet dislocation or wet diffusion?
The first one we did was wet dislocation. So now, in order to make this equality and solve for it, all right, let me back up. Make sure you guys understood what we're doing. This is the total strain rate, and this is the dislocation creep component and the diffusion creep component. I want to draw a line that shows where these two things are equal to each other. So I just take that thing and equate it to that thing. And I want to make a log-log plot where I plot the log of stress versus the log of grain size. So A prime is equal to all this junk. And I didn't want to write it out just because you can see what the values are, and you could just write it as a variable in your Excel file or MATLAB file. So now we have to do the same thing for diffusion creep. So, and in this case, it's going to be B instead of A. Right? It's right here. Oh, I see. I understand. This is... Jesus Christ. I see why you're confused. I'm sorry. That shouldn't even be there. For dislocation creep, that's not there. Aha! The source of the confusion. Yeah, I see your confusion.
So the end use for that is 3.5 from the base.
That's right.
And so you were saying that percent A is given in other units or something?
That,
Or do you think that changes?
that's right. So what you need to make sure, when you do this kind of thing, you need to make sure that whatever units of stress you're using, that the A has the same units, right?
And typically, what are the changes that be? What are the parameters that could be in another unit? Let's say
They might be in pascals or gigapascals or kilobars or something like that. Yeah. All right. So you guys, are you rolling now? That's right. So then you're going to write, this is an equation, y equals mx, where you're going to use d as x to get that equation. So you can see, what is b? All right, someone tell me what b is. So, diffusion creep. All right, so b is 1 times 10 to the 6th. And then this r thing is 1. So it's going to be that thing times 1,000 times exponential of minus 335. Now, the activation volume is 4. So you get 2 times 10 to the 9th pascals times 4 times 10 to the minus 6. Divided by 8.314 times 1473.
What did it take for the volume?
What's that?
What did you choose for the volume? 4?
4 times 10 to the minus 6.
Okay.
All right, so has someone calculated A and B yet? Yeah. That's this. That's right. That's right. Does that help? Yeah. All right.
So what times?
All right. I'll get it, and I'll see if you guys get the same thing. Ah, shit, what did I do wrong? All right, so who got A prime is equal to 5.6 times 10 to the minus 13? Yes! Unbelievable. All right. What was it again? 5.6 times 10 to the minus 13. Is it minus or positive 13? That will make a big difference. Okay. So you guys follow how I did that? I mean, that's really hard math there. All right, so B is 1 times 10 to the 6 times 1,000 times exponential of So who got B is equal to 6.8 times 10 to the minus 4? All right, you guys getting those numbers? Is anyone not getting those numbers and wants to get them? Yeah.
In the first equation for A prime,
Yep.
is 90 and 1,000
Yep.
to 1.2.
Yeah, it's 1,000 to 1.2. Yeah. Yep. All right. So this is the water. This is the water content. All right. So if you made a plot of strain rate as a function of water content, and you fit all the data, you get it that it's almost linear, but the data are better fit with the exponent being a little bit bigger than 1. Okay. So go back to the So you guys have your A's and B's. So I should be able now. I can do that. I don't know how you guys do this in MATLAB, but let me see here. So
How much do you want to vary E?
what's that?
How much do you want to vary the grain size?
We want to go from. All right. So this is you're gonna have to be careful here.
This is in millimeters, right?
This is in millimeters. That's right. And B is in microns. So you want to. Yeah. Sorry. Yes. Look in the. So if you look, this is awesome. This is like real time how people screw this up all the time. So if you look in this table, people. So if you look in this thing, it says, do you see right here where it says wet dislocation creep or wet diffusion creep, the subscript C, come down here, and it says, or this A, this footnote here. This is for stress and MPa, water fugacity and MPa. Thank God we're not doing that. COH and hydrogens per 10 to the 6 silicons, and grain size in microns. Right? And so you can see what this A thing is, right? It's just a fitting parameter, but it has to have the units. You have to have the units right because you're taking some flow law that has temperature and stress and MPAs and grain size and some units, and you have to get something that has units of 1 per second. So if I gave you A and that had units that were microns, and you put a millimeter in it, you'd be wrong because the grain size exponent is the cubed. You'd be wrong by 3 orders of magnitude. So, or not 3, 9 orders of magnitude. So you'd be really screwed up. And then you would say, oh, these flow laws are wrong. I'm not going to do this. Right? So you'd get a viscosity of whatever, 10 to the 30th or something. And you'd say, Jesus, what's going on here? All right. So you guys all caught up? You ready to make this great plot? All right. Who's already done it? Nobody? All right. All right, so I'll do it in here, and you guys can try to follow on with whatever thing you're doing. So if I was doing this, I don't know if you can do this in MATLAB or Excel. I know you can do it kind of, but I'm just going to set a variable A prime equal to 5.6 times 10 to the minus 13. So then in Excel, you would just have some cell that had that number in it, right? Set variable B equal to 6.9 times 10 to the minus 4. So then all I need to do is I'm just going to create a matrix of y that is equal to b divided by a prime divided by, what's that? What? Because I didn't need to make it a B prime because the flow law had A in it, right? Right. I just made the prime just so there weren't two A's. This is awesome.
And you want D and what units?
Microns, yeah. So the plot was from 100 microns to where did it go? (10 to the 2 millimeters). So that's 10 to the 5th. All right. So you guys can all write an equation like that in some thing that you have on your computer, right?
Was it log plot?
Yeah. So I'm going to now. What I would do, I don't know how you would do this, but you have lots of time to still do it. And then I'm going to turn it into millimeters. So I'm going to say the log of x divided by 1,000. So this is something that you could do really easily in Excel, right? I mean, I could be trying to do it in Excel, but how many of you guys are using MATLAB to do this? So you can do the same thing in MATLAB, right? Yeah, okay.
What is that n?
Yeah, we have to set n. So what is n, everybody? So n is the stress exponent for dislocation creep. What's that? It's microns, yeah. So I converted it to millimeters right here. Because I just, here, I made this, in this stupid program, I'm making this matrix with x from 1,000 to 10 to the 5. And then to plot it, I'm going to let x equal to x divided by 1,000 and take the log of it. That's right. That to make the plot the same as the one I showed you. So you guys have it? So who's going to win the race? Has anyone done it? You got it? All right. Hey, I got it right. Unbelievable. Yeah. Well, now when they're done, they'll have whatever file, and they can do this with whatever flow they want to do. You get it? So just give me a hand raise when you get it plotted. So did you get that the stress is 1 MPa at 1 millimeter?
Yes.
All right. You got it too? All right. All right, I'll make mine a little bit fancier. All right, you nailed it.
What did I nail it?
You got you plotted a line. It's log, yeah.
So it's millimeters against stress.
In megapascals. You got it? All right. So So is this the... This is awesome.
And this is for 1 part per millimeter.
This is for 1,000 ppm, 1,200 degrees C, and a pressure of 2 GPa. Olivine. Do you get it, Beth Ann? All right. You got it.
Well, I'm sorry it's not easy.
I don't think it should be hurt. So if you're here, you're in dislocation creep. If you're here, you're in raise your hand if you need more time. All right. You're close. That's right. I'll go back to the equation here. Got it? Got it? We're going to draw a strain rate constant. 45 minutes. The next step will be much easier. So you guys already have A and B.
It is 3. The minus 1 comes from this guy.
So by the way, this thing that you're done, you can use this for any material now. All you have to do is put in the right values for those parameters. Having issues. Everyone got it? You still have issues?
I don't know why.
Got it. All right, who else is still having issues? Anyone else still stuck? Okay. Your computer's just wrong. So now what the heck is this thing? You want me to put my microphone back on? All right. I think the battery might be dying. So anyway, so what you've now done is made a plot of stress versus grain size for 60 kilometers down in the mantle at a temperature of 1200 degrees. And down here, where the grain size is small and the stress is low, you would have diffusion creep dominating. And if the stress was high or the grain size was really big, you'd have dislocation creep. But you don't really know yet what the viscosity is. So what we want to do now is put on a contour for a strain rate. So what strain rate? Let's use a strain rate of 10 to the minus 14. Does that sound like a good one to use? Okay, so now I'm going to show you a trick. You're like, oh no, not a trick. All right. So if I write this, strain rate equals A prime sigma to 3.5 plus B times sigma over d cubed. And I want to make it as a plot of sigma versus grain size. I have a hideous problem because I'd have to factor out the sigmas and figure all the polynomials out, and it would take forever. But all you have to do is in your head say, well, wait a second. What I can do instead, this is a trick that you can do all the time when you're dealing with this kind of nonlinear equations and you haven't taken algebra since 11th grade. You can use your computer to do it really fast. And you don't want to use a root finder. You just flip the equation around because you can write it instead. You can write it easily enough as grain size is a function of stress and then just exchange the variables. All right? Does that make sense to you? So what I'm going to do is solve this for grain size, which I can do. But that's not what the plot is. Right? The y-axis is stress. So I'll solve it for grain size as a function of stress, and then I'll just let x equal y and let y equals x and plot it, and it will work. All right? So that's simple algebra. So I have strain rate minus A prime sigma to 3.5 equals B sigma over d cubed.
That's B prime again, right?
This is whatever that thing that we calculated, and I gave you the number.
But I mean to keep the number.
Did you guys end up calling that B prime, that thing?
No. Okay.
Whatever you call it. All right. So then d cubed equals B sigma over strain rate minus A sigma to 3.5. So D equals B sigma over strain rate minus A prime sigma to 3.5 to the 1/3. So that is going to be the thing that you're going to do now. So now this is where you have to watch out, because what you want to end up with is this thing. So it's going to have this shape, like that. All right, so now look what's going to happen. You have to watch out, because if you do this to a sigma, if you make that plot to a sigma where there is absolutely no component of diffusion creep anymore, then your denominator will go to 0 and the thing will blow up and you won't understand why it's not working. So what you have to do is you need to set a strain rate. So we said set strain rate equal to 10 to the minus 14. And we're going to do it from a stress of 10 to the minus 2 to a bigger number. And what we want to do is set it so that it's the dislocation creep at a stress that you get 10 to the minus 14. Right? And then I'm just going to subtract a little bit from that so it will plot without blowing up. All right? So in your MATLAB script, you'll do this equation from sigma equals, what did we say? 10 to the minus 2 to sigma equal So if I didn't subtract epsilon from this, then this sigma would equal the stress for dislocation creep. And if I plug that in there, this would be 0 and it would blow up. So what I want you to just do is do it from sigma equals that, and then make epsilon some really teeny number, like 10 to the minus 5 or something. Okay? So who doesn't understand what the heck I just did? Or do you want me to repeat it? Okay, so you guys understand this equation, right? You got that okay? So that's the equation we're going to plot. And then when you're going to have a matrix, right, of stress and grain size, and you just want to flip them, right? And then that will give you that curve. So this is just a trick that you can do with a computer. It's really simple. All right? And so I was just warning you that if you make strain rate equal if you make this strain rate equal the dislocation creep strain rate at high stress, that this will go to 0, and that you will screw up your plotting program. So just take this, plot it from this number minus a little bit. All right? And this is 3.5. And then you should get a curve that does this. And that really should only take you less time than it did the first part, hopefully. And then they're off. And I'm a roving reporter if anyone wants a